Much appreciated. Dear Heavenly Father, we thank you for this day. Thank you for the rain finally letting up. Just help us to glorify you and what we do this day. Help us to just make the most of this time together, Lord. In your name I pray. Amen. Okay, so I wanted to show you guys another wave equation problem. This one is pretty, this problem I think you can sort of understand physically. Like maybe you've even tried this sometime, right? Imagine you have a wall somewhere, right? Just for convenience, I'm going to say that this is y equals to 0, right? And, you know, oh, I'm sorry. I don't mean to give Mr. Farrell one of them Farrell hats, or Mr. Top Hat, proper hat. And then, you know, I'm not very good drawing hands, but you can imagine that he's got this rope, right? You know, he's got this rope, right? And I think you know what happens if the rope is stretched really tight. What happens when Mr. Top Hat takes the rope and does one of these deals? Yeah, well, it hits the wall and comes back. But imagine that the wall was infinitely far away. It would just keep going, right? I mean, but you got the right idea, right? However you sort of perturb the string, that will go on, right? So if I did like 3 short bursts, then you'd have like kind of like a wiggle, and then you just kind of travel that way, right? So let's try to solve this problem mathematically and see if the wave equation actually bears out your intuition. This problem, it's in lots of books. It's really one of the centerpieces of this technique of using Laplace transforms to solve partial differential equations. Not a required topic in here. There's not really technical support for it in your book, let's say. And it's awful easy to make up simple problems which are really hard to solve in this world of things. So this problem is very precious in that it's so simple. So here's the PDE that I want to solve. The wave equation, partial squared u partial t squared equals to c squared partial squared u partial x squared, like that. And the boundary condition that we got is u of 0 comma t equals to f of t. So what that's describing is where this point is right here, right? This is, and I said u. Did I say y? I meant u. Let me just accept my fate. I'm going to call y equal to u here, all right? So that's, you know, u of 0 comma t is basically just how he's making the string wave up and down, right? And we also have initial conditions, and this is for t greater than 0, right? And we also have initial conditions, which is that originally you start out with the string at 0, and it's also at rest. So kind of boring, but this just says initially at rest, all right? So I think we all understand the problem. We got a string, we pull it really, really tight. It starts out at rest, and then we start wiggling the one end and seeing what happens as a consequence. Okay, so physical constraint. We're going to suppose that the limit as x goes to infinity of u of x comma t is equal to 0. All right. Don't think about that too hard. I find that very troubling. If the wave pulse goes on and on, how is that consistent with this limit? But whatever. This is elementary applied partial differential equations with Fourier series and boundary value problems by Richard Haberman. I have done some independent study courses out of this, like 1 or 2, and it's a decent book. I think I spent like $5 for this, so well worth it. No, it's a good book. I mean, but it's a nice like second book to read past the one you have. It's got a lot in it. I'm still not entirely sold on what's the best second book past where Nagel, Staff, and Snyder is a great book for this course. I don't know what the greatest next book in differential equations is to recommend to you guys. I don't have a good strong opinion on that. Anyway, maybe you're like, well, one will do, so don't worry about it. Okay, don't be that way. I'm right here. You hurt me with that. Let's see here. Okay, so we have this this differential equation, right? Partial squared u partial t squared equals to c squared partial squared u partial x squared. And what I want to do is, like I said, I was going to use the Laplace transform. So which am I going to take the Laplace transform of? I mean, in principle, you could take the Laplace transform of either x or t in principle. But as to not be weird, we're going to take the Laplace transform of the t variable while holding the x variable fixed. That's the idea here. Take Laplace transform of the t variable. I mean, with respect to the t variable, I should really say. Holding x fixed. All right, so if I take the Laplace transform of u, which is a function of originally x and t, let's say, right? Then that gives me a new thing, which will denote big U of x and s. Except usually I won't write the x comma s, I'll just write big U. I guess I might write both variables. There's not too much writing to reduce the confusion. That will be defined to be the integral from 0 to infinity of e to the minus st u of x comma t dt, like normal, right? The only thing that's different here is we've got this x dependence running around waiting to get us in trouble, right? So now that we've set the rules of the game, you take the Laplace transform of the wave equation, what happens? So second derivative, we know how to take Laplace transform of y prime prime, right? We get what? We get s squared, big U, right? I mean, I should say u prime prime. And then minus what? Minus initial condition terms, right? What happened to the initial conditions, though? They're both 0, so that's it for the left-hand side. On the other side, we've got c squared, the integral from 0 to infinity of, partial squared u, partial x squared, e to the minus st dt. Because that's the Laplace transform, right? Now here's the sneaky step. This is a partial differentiation with respect to x. The integration is with respect to time. These are independent. So, by analysis we've never justified, nor will, you can pull the partial derivative outside. But this is the sort of thing that Math 431 would at least get you in the neighborhood of being able to prove. You need something called uniform convergence. It's not a big deal. I mean, it's kind of a big deal. Big deal for mathematicians, not a big deal for you guys. Here. Anyway, so we pull the partial derivatives out of the integration over t, and what do you got? This animal's what? That's just big U. right? So what we got then is we've got c squared partial squared big U partial x squared. Let me rewrite that in a somewhat suggestive fashion. So what we got is we've got U prime prime minus S over C. Is that right? Yeah, S over C quantity squared, big U, equal to 0. Do we know anything else about this big U? What have we? We haven't used the boundary condition yet, have we? But we can take the Laplace transform of the boundary condition also, right? So the boundary condition was, what was it? I can't read. U of 0t equal to f of t. So take the Laplace transform of the boundary condition. What you got? You got yourself a big U of 0, comma s equal to the Laplace transform of little f, which we'll call big F, as usual. Yeah. So in other words, if I can just omit, well, I won't omit it. Fine. If you want me to be, this is, oh, I don't know a good notation for this stupid thing. I mean, in gory detail, this is partial squared U partial x squared of x comma s, right? Minus s over c quantity squared U of x comma s equal to 0. And we just figured out that the initial, in the x sense, initial, x equal to 0 comma s is equal to f of s, right? And so this is for all s. Let's say greater than 0. I think we need s greater than 0. I don't know. Let's just say for all s. That makes sense. Don't ask me what those are. So that, what's that? Well, that's a garden variety, what? That's just a plain old ordinary differential equation if you ignore the fact that s is a variable, right? Just think of s as a constant, hold s fixed here. We can solve that with respect to x, right? What are the solutions? The solutions are Cauchys and Cinches. Yeah? So this has solution big U is equal to like, oh, I guess I'll write it in terms of exponentials, yeah? So this is C1 e to the minus s over c times, I've forgotten my x. Where'd my x go? So minus s times x over c plus c2 e to the s times x over c. All right? That's U of x comma s. But of course, we have two things actually to use here, right? The one is this, right? But the other thing we also know is that. And, well, yeah, that's, okay, fine. It's a little slippery, isn't it? I guess I don't need that. I needed that to take the Laplace transform. Never mind. Let's focus on this one here. What's that give me? I'm sorry. I'm missing something here all of a sudden. Well, you can, okay, apparently you can argue that this implies that the limit as x goes to infinity of u bar of x comma s is equal to 0. Now, if you have that, that forces one of these constants to be 0. Which one? C is a positive constant here, okay? So as x goes to infinity, C is a positive constant. We're going to make s greater than 0 for the sake of not going nuts. So s being greater than 0, x being going to infinity, and c being positive constant, this guy blows up, right? And so we need C2 to be 0 to satisfy these conditions over here, which I have not begun to really explain to you. Sorry about that. So we're just left with that term. And what happens when we plug in 0? Yeah, we get C1 equals to f of s. Well, that's interesting. So therefore, big U of, what was it? xs is equal to, what is it? It is f of s e to the, what was it? Minus s times x over c, right? So to solve this problem, I need to get back to the time domain, right? So what do? We have a product of two things, right? We know the inverse, what's the inverse Laplace transform of big F? Right? It's little f. And what's the, oh, well, that's it, right? I mean, that's all we need. I was about to say I need convolution here, but that's nonsense. We don't need convolution. We got a theorem for this one, right? The inverse Laplace transform of this, u of xt, is equal to, what is it? It is equal to f of t minus what? Right, minus s over c. Then the unit, oh man. Yeah, yes, x over c. Thank you, Travis, very helpful. And at this point, I realize why we should have been using y the whole time. Is it too late to fix? See, because we use u for unit step function in here, which that book doesn't. So yeah, we need a different, let's say theta. Yeah, exactly.
Okay.
Oh.
I thought you were going to change
Wow.
all of the u's.
You have powers, apparently. You made me think that. Let's see here. So t minus x over c. So be careful around Danica. She might put thoughts in your mind. Let's see here. Yeah, I think that'll do. So the step function, no? I feel like you were easier to aggravate in previous semesters. You've gotten more chill lately. Trying? Okay. So fun. Yeah, so that would be the answer. And does this, oh man, this makes so much sense. If you look at what this is, what is f of, what is this? I mean, let me rewrite that. That's, how can I write that in a way which is more understandable? How to explain this? Man. Let's see here. I need to introduce another function like g of, maybe if I introduce g of x, which is equal to f of x over c or something like that. No, g of, how's it go? Curses. I'm trying to rewrite this so you can see more clearly what's going on here. What happened? What t minus x over c equals to 0? What is that? Yeah, I just can't find the words today. I mean, solve that for x. What do you get? X equals to ct, right? So let me put it into words here. F of 0 moves to x equals to ct at time t. So what that's saying is that the solution is just like we expected at the beginning, right? Whatever you do at time, whatever you do at time 0, it just propagates outward like that. Now these conditions start to make sense if you don't keep waving the string forever, right? If you just do it for a short time, do you ever actually get to infinity? No, so it's always 0 if you go far enough out, right? So as long as you don't keep wiggling the string too long, these boundary conditions make sense. As long as it's sort of a disturbance in the string over a finite period of time, these conditions are reasonable. And this shows that whatever you do at time 0, it just propagates out. Whatever shape you sort of trace out at the start of the string, it will, if I, well, anyway, does that make sense? I think the more interesting thing here is that we just solved the differential equation, a partial differential equation using a Laplace transform, right? This is quite different than our other method, isn't it? And also, just to emphasize, that is the solution right here. It says that basically whatever the function looks like at time 0, it just kind of propagates out with speed c, which makes sense. Well, yeah, if c was the speed of light, then it'd be fast, and a rather interesting string, I think. Was that? Did you get a punch? Was that a Zach punch? What was that? I wasn't paying. I don't know. This is a silly place. I should stop. This is the other really different thing here is we didn't solve like a standing wave pattern, right? We're not looking for how the wave is behaving when it's tied to 2 points, right? That's what we did last time. This, we let one end just go on and on, right? It's for an infinite domain. So that's kind of a typical thing. If you're trying to solve a wave equation on an infinite, like a half-infinite domain, like we just did here, maybe the Laplace transform is the right tool. Yeah.
In general, what kind of things should we look for in boundary and initial conditions to say oh, that's something we should solve with Laplace instead of our other method?
Yeah, I don't know. When to use this method, I have no earthly idea. I don't have enough life experience to answer that question, unfortunately. But that's a good question. That's an important question that I wish I could answer. But I don't know. There's also something called a Fourier transform, not to be confused with the Fourier series. Fourier transform is something else. Instead of integrating with respect to e to the minus st, you integrate with respect to e to the ikx or something like that, where that's the imaginary exponential. This gives you the Fourier transform, and that's a whole other tool that you can use to solve partial differential equations, which anyway, to do that method justice, you need to have taken and mastered complex analysis, because it involves contour integration to meaningfully understand it, which is not something that is, well, it's not something that's impossible to master, but it will take you some time. Complex integration is an acquired skill. It's not a, it takes some time to get used to how you take integrals with respect to complex variables. There's a lot of things to learn there. I think our math 331 course is a good start. I wouldn't say it's the finish, because there's no end to complex integration theory. All right, back to Laplace's equation. So finally, our third and final PDE. So Laplace's equation, I told you before, is generically nabla squared. U equals to 0. Now, for us, we're going to look at it, I think, in the plane, at least for to start with here. So here's the problem. I'll state the problem for us to solve. We want to solve partial squared u, partial x squared plus partial squared u, partial y squared equal to 0. That's Laplace's equation in the plane. And given, so we've got some things that we know about this u. Partial u, partial x at 0y is equal to partial u, partial x at pi y. Those are both 0, thankfully. And that's for 0 less than or equal to y less than or equal to 1. So we're looking at some sort of rectangular domain. All right, let me draw a picture of what's going on. Apparently x is ranging from 0 to pi, and y is ranging from 0 to 1, so we're trying to solve Laplace's equation on this rectangle, basically like that. And what I've just told you is that the derivatives of u are 0 where? So, just emphasize this and this are here, right? And here. We're given that the derivatives are 0 there. So some of you are electrical engineers, so you're supposed to care that this equation, right, is what? It's the divergence of the gradient of u. The meaning of this, if we can put a minus here, if you don't mind, well, this is exactly the divergence of the electric field, right? So saying that this is equal to 0, remember Maxwell's equation, Gauss's law in differential form is that this is the charge density divided by epsilon naught, right? So we're solving for the voltage function in the absence of charge in this rectangle, right? What does this boundary condition, partial u partial x equal to 0, mean in terms of electrostatics? What is this in terms of the electric field? This is saying what? So the electric field, right, is what? It's minus partial u partial x minus partial u partial y. That's what the electric field is. In terms of it's minus the gradient of the voltage function. So when I say partial u partial x is 0 on the edges, what am I saying about the electric field? Away from the, let's see, it's flowing away. I think it would mean that the electric field, if it's non-zero, it has to line up with the edge, right? But more to the point, the perpendicular, it says the x component to the electric field is equal to 0, right? I think that's what you're saying, Zach, right? No? It's the part of the electric field which is perpendicular to the surface is 0 here and here. How would that happen? How would you have an electric field which is perpendicular to a surface? When would that happen?
It's going in a constant direction inside the area.
How about this? What if I have metal, right? Then what did we say about the electric field as it gets to the surface of metal? Metal has free electrons, right? It is ions, things charged that can be pushed around. So if the electric field was anything like except for that, then you'd actually have electric field pushing the, you'd have currents inside your metal. So if it's in static equilibrium, which we're assuming here, then the electric field has to be perpendicular to the surface of the metal, right? So one way you could achieve these boundary conditions would be to have metal on the edges of the rectangle. Does that make sense? All right. I'm just trying to make it not just a math problem for you guys, just if you don't mind. I realize that Physics 232 is not a prerequisite for this course, but the fact is many of you have had it, right? Or you're currently having it, and you've had it. You've had it, but it fades. All right. Well, let's go on here. What are the other? I mean, there's two more sides to pin down, right? How about this and that, right? So there we have what? We have. So now I'm going to tell you, we're going to set the voltage to be 0 at the top. So up here, we have U of x comma 1 equals to 0. So maybe you ground the top, right? The top is grounded or something like that. We set the voltage to be 0 on the top. And then finally, the interesting part. Down here, we're given a somewhat interesting voltage distribution down here, U of x comma 0. And here we have U of x comma 0 equal to, according to my problem, 4 cosine 6x plus cosine 7x. Admittedly, this formula is just for our mathematical convenience, so that as we work out this problem, it's in a good illustration of the mathematical techniques. I wouldn't say that this is maybe the most physically interesting voltage distribution on the bottom, right? Maybe a more interesting voltage distribution is something like I have, 0 voltage on the corners and it like spikes up to some, voltage in the middle and linearly decreases, something like that. I mean, you can imagine other voltage distributions that you could arrange by resistances or something on the edge, right? So we want to solve this problem. So what are we going to do? I think hopefully you understand the problem, right? Where are the initial conditions? Trick question. There are no initial conditions. This problem's timeless, right? This is a problem in electrostatics. There's no time. Everything, all the time dependence is gone. The electrons or whatever, they've gone to where they need to be on the edge of things. Or everything, all those sorts of transient behaviors are done. It's in electrostatic equilibrium. Okay. So what do you guys think? What should we do? So this problem only has boundary conditions is kind of the interesting thing. It just has enough of them that we can solve it. Anyone care to make an Ansatz? That's German for guess, y'all. No? No Germans? No one here believes in educated guessing? 17. Interesting. How about you, Vice President? Anything? 1.
0.
You guys, I can make more problems on the take-home, Let's see here. How about this? We write our solution as x of x times y of y, right? That's what we did to solve the wave equation, and that's what we did to solve the heat equation before it. We proposed that our solution was a product of solutions of functions of one variable. That same sneaky trick is going to work here. So when you plug in this product solution into Laplace's equation, what do we get? That gives us like x prime prime y plus x y prime prime equal to 0, which of course gives us that x prime prime over x is equal to minus y prime prime over y. As usual, we go, well, what do you know? That's a function of x, right? Over here, you got what? Function of y. The only thing that's constant, the only thing that's common to both functions of x and functions of y, the middle ground here is just plain old garden variety constants. So we solve this equal to some constant k. I can't remember if I should make that a plus or minus k. It doesn't really matter. This much you can see. Given the sign difference there, SIGN, you should be able to see, right? If we've got cosine and sine for x, what are we going to have for y? What's the interplay here? If x is in cosine and sine, y is going to be in cosine sinh of the same sort of argument. And vice versa. If x is cosine sinh, then y is going to be sines and cosines. So this problem necessarily is going to involve hyperbolic sine, cosine, and sine and cosine by the same sort of multiplication. Now, let's see here. What should we pick on? It looks like the y boundary conditions are kind of complicated, aren't they? Like this is more or less x of x. I mean, let me write it here. This is x of x, right? Times y of 0, right? And this up here is x of x times y of 1, right? And so that's a little bit messy. On the flip side, these side conditions look like they're going to make pretty nice boundary conditions for x, right? So in particular, partial u, partial x, 0y equal to 0, and partial u, partial x at, what was it, pi y equal to 0 imply what about my x? This implies x prime of 0 times y of y equal to 0, and x prime of what? X prime of pi times y of y equals to 0. So we can glean from our side conditions, if you will, the following, conditions for the x solution. We need x prime of 0 is 0, and we need x prime of pi be 0. Now you go back to my chapter if you want, or you just go back to basic principles. This would be the second proposition in my notes. That's where I solved it. Originally it was going to be insulated endpoint heat equation problem, but I mean, it no longer has that interpretation here, but yeah, the solution is going to be not sines, but cosines. So let's see here. In other words, it's going to be k equals to minus beta squared, I think, which is, of course, going to be less than 0, right? So this gives us x prime prime. I'm sorry, let me just take a breath here. We get two equations, right? What are those two equations? X prime prime minus k x equal to 0, and y prime prime plus the big K times y equal to 0. These two I got to solve, right? So I'm suggesting we work on the x one first, and I'm suggesting that the interesting case is going to be the case that k is the case that k is negative, because if k is positive, then x is cosine sinh, and it's not hard to see that we're not going to get an interesting solution out of that. And the constant solution is not interesting either. So the k negative solution is where it's at. All right. All right. So this is x prime prime plus beta squared x equal to 0. So we can solve that. That gives us x is equal to something like a cosine beta x plus b sine beta x, right? And then x prime is what? Minus a beta sine beta x plus b beta cosine beta x, yeah? So let's plug in 0 and pi, see what happens. What happens when we plug in 0? We get a b beta cosine 0, right, which is 0. So that just tells me that b is 0, right? We're assuming that beta is non-zero, okay? So it must be that b is 0. What does that leave us with? Leaves us with x prime of pi, which is going to be minus a beta sine of beta pi. Now that has to be 0. How can that be 0? If a is 0, we're out of luck. That means that if a is 0, the whole solution's 0. We don't care about that. Beta is non-zero. It must be that the sine is 0, right? So what does that force on us? Beta pi is equal to n pi for some n in the natural numbers. I'm assuming beta is positive, so I don't need to look at negative solutions here. So, yeah, beta is equal to n. And that means that my k is actually minus n squared. So in summary, we've just found that like the nth x solution is something like cosine, yeah, nx. That's half of it. Now what else do we need? By the way, if you thirst for more knowledge about this, you might look at MIT's OpenCourseWare. You might find something there. They do have higher differential equations courses. Some of them are taped. You know, I think even their ordinary differential equations course, you'll learn a lot if you watch those videos. They're pretty awesome. I certainly have when I have. All right, so where am I? So I figured out what n is, which means I figured out what I figured out what k is. So now we're back to the y equation. We've got y prime prime. Right? What is it? Y prime prime plus or what? Oh, minus n squared, right? Y equals to 0. What's the solution to this? We got a, let's say a sub n cosh of ny plus b sub n sinh of ny, right? I think you can see from the upper edge here that we need y of 1 is 0, right? So, I mean, there's a couple different ways you could go here. I tell you what, I won't do that. I'll just construct the formal solution at this point. Hence, we construct, what was that, my notation? U of xt equal to the sum n equals 1 to infinity of a sub n cosh ny cosine nx plus b sub n sinh of ny cosine of nx. So all I did there, guys, was multiply my product solutions and then take an infinite series of them. These coefficients, a sub n and b sub n, hopefully are enough freedom for us to fit the remaining boundary conditions. I suggest we start with the green one, because I think that one's the easier one, right? What would happen? What happens if we impose the, any questions? Yeah.
Are we introducing d here now?
There's no, oh, goodness gracious. That's, yeah, that's just me. So that's supposed to be a y. It's a very timely mistake. Let's see here. But, sorry, that was awful. I blame Danica. Let's see here. You're fine with that? It's Danica made me do it. She put the thought in my mind. It's like an episode I saw of Airwolf the other day. Let's see here. U of, they're rerunning Airwolf, you know. Well, you guys wouldn't care. But anyway, most awesome helicopter ever. U of, where was I? X1. Although my children don't quite buy into it. They're like, what's so awesome about this helicopter? I'm like, it's Airwolf. It's the most awesome helicopter ever. And they're just like, but it's just a helicopter. I'm like, no, it's Airwolf. It's not just a helicopter. They just don't appreciate things. I don't know. I guess it's kind of like how I don't entirely appreciate Pokemon. Let's see here. N equals 1 to infinity. Plug in. I put in y. Put y equal to 1. Oh, you know what? This is interesting. This actually is not as. I mean, it's okay, but it's just not what I was thinking it was. So, an. What we got? We got cosh. Cosh of n, right? All right, I'll allow it. Danica could probably make him do it. Let's see here. Cosh n cosine nx plus b sub n sinh n cosine nx. What's this all equal to? Please let it be equal to 0. 0, thank you. So if this is equal to 0, we could have factored out the cosine nx like civilized human beings a second ago here. What would that tell us? Did I give you guys a 2-dimensional Laplace problem or a 3-dimensional Laplace problem? Yeah. 2? Just, is it exactly this one?
It's very similar.
Oh, okay. Well, that similar is okay with me. Exactly the same. That would be no fun. Okay, well, that's fine. So if this is going to be equal to 0, then that means that every coefficient here must be 0, which gives us what? It gives us that an cosh n plus bn sinh n is 0 for each n, right? So you can, I mean, you can pick which one. Let's see here. Well, let me just say that. All right. That's there. We can come back to this. So let's use our other boundary condition, the remaining one. What does that tell us? You know you're really doing something when it takes you all of the boards you have and then some to do a problem, right? Like, I love these problems. I remember as undergraduate first working them and getting done with a problem and then looking back at my work and realized that I had just filled up 3 pages for a single problem. It's like these, I don't know. If you actually work through all the details, right? I mean, and all the things that could have happened but didn't happen, it starts to fill up a lot of space. Okay, so U, and these aren't the worst ones of these either, guys. Like, these are homogeneous boundary conditions. There's also non-homogeneous boundary conditions, which might be what you actually need to solve for a real-world problem. You know? There's more to learn here. 6x plus cosine of 7x. Now that is given. That's our given boundary condition, but we can apply that to our sort of, this is the analog of what I was calling the blank template last time, right? So this is like my blank template solution to give it a name. And so if I plug in x0, what happens when you put y equal to 0 into sinh y? Sinh of 0 is? 0, right. So we just have the cosh-cos term. So we have u of x0 is the sum. N equals 1 to infinity of, what was it, a sub n cosh of 0, right? Cosine of nx. cosh of 0 is just 1, all right? So, on the other hand, that's equal to 4 cosine of 6x plus cosine of 7x. This is wonderful because this is already a Fourier expansion of the boundary condition, right? We've already got, we're given a Fourier cosine expansion of the boundary condition, which means we don't actually have to go through and calculate the Fourier expansion of the boundary condition, right? If this had been something else, I might have to actually find a Fourier expansion of it so that I could equate it to my blank template solution and pick out coefficients, yeah? So what can you extract from this? A sub n is equal to 0 for n not equal to 6 or 7. And what's a sub 6 equal to? And what's a sub 7 equal to? I got a 4 and I got a 1. Very good, yeah. But then we can figure out the b's, right? Because, by the way, this implies that b sub n is equal to 0 for n not equal to 6 or 7, right, by star. We call this thing star, right? Because, I mean, you can solve this for b sub n. B sub n equals to what? B sub n equal to a sub n divided by hyperbolic tangent of n. Good news, that's non-zero. So if the a sub n is 0, the b sub n is 0. On the other hand, if a6 is 4, that says that b6 is what? Four over. All right. Let me write it in terms of. I'll write it in terms of coshs and cinches. So it's 4. I'm sorry. Let me put that hyperbolic tangent away. A sub n cosh of n over the sinh of n. So that's 4 cosh of what? Yeah, cosh of 6 divided by the sinh of 6. And likewise, b sub 7 is, well, cosh 7 divided by sinh 7. Right? Okay, so we can write down our answer. U of xy equals to, let's see here what we got. We got 4 copies of a, so that's a6 is 4. Then I got what? I've got cosh 6y. What is it? Cosine 6x? Right? Then what? Plus sorry, I've lost my place. Cosh of 7y cosine of 7x, right? I'll just write both of the a terms down to start with. Then the b terms, we got what? We got plus 4 cosh of 6 sinh of 7y divided by the sinh of 6 cosine of 6x plus the b7 term, which is going to give us cosh 7 sinh 7y. What's that? I'll get out of the way here in just a second. What do you say? Yes, thank you. Now, of course, you can group things together here, right? Like, if you look at this, we can clean this answer up a little bit. We've got 4 cosh of 6y. I'll factor out the 4. Well, should I factor out the, yeah, I'll factor out the 4. Cosh of 6y plus cosh of 6 sinh of 6y divided by the sinh of 6 times the cosine of 6x, and then plus parentheses, let's see here, cosh 7y plus the cosh of 7 sinh of 7y over sinh of 7 cosine 7x. And that is minus 4 cosine of 6x divided by the sinh of 6 times the sinh of 6y minus 6 minus the cosine of 7x divided by the sinh of 7 times the sinh of 7y minus 7. There you go. That's a good form of the answer right there. See, there's adding angles formulas for cosh and sinh. So like sinh of 6y minus 6, for example, is sinh of 6y cosh of minus 6 plus cosh of 6y sinh of minus 6. But that's equal to, you know, cosh of 6 sinh of 6y minus sinh of 6 cosh of 6y. So if you can look at what we have here, right? Imagine expanding the sinh of 6y minus 6 and then dividing this by, if you divide this by minus, maybe I lost a minus in here somewhere. I think I lost a minus. Where did I know where I lost it too, don't you? See where I lost it? Right here, right? See that? Minus. Minus. Minus here. Minus here. Right? Where else does that puts a minus where? These were the b terms, right? So it puts a minus on this guy, a minus on this guy, minus here, minus there. This problem we're looking at is actually an odd problem in the book. I'm working out actually number 1 from section 10.7 in your text in gory detail. This is it. And, you know, when I first worked this problem, I got to the answer, you know, like up here. And then I was like, yes. And then I look in the answer key and I'm like, what? And then, you know, a half hour of hyperbolic trigonometry later, I realized, oh, they did this. So your book takes great joy in using hyperbolic trigonometry that you don't know to hide answers that you've already found from you in plain sight. Now this is a nice answer though, because you can see some of the things that were given to you by just plugging in values into that formula. It's pretty nice. For example, if you put y equals to 1 into this formula, what happens? You get sinh of 0.